All right, so in the examples so far, we kind of used a small number of subintervals, or when we looked at that area calculation, we used a small number of approximating rectangles. And, well, actually, let's take a look at it. We used n equals 3 here. And you can kind of see it gives a rough, not too bad approximation for what the area under the curve might be. But it's an approximation. So when you're looking at this, going back to this example we did, it's an approximation. So there's sections here that we kind of missed in our calculations. We didn't account for that. But then there's other sections where we kind of did too much, like right here, over here. Those are sections that were inside our rectangle, but not really under the curve. And so, there's portions where we didn't do enough, and then there's portions where we did too much. So these are, in the end, these are approximations, but we can make them better. So we can get these more accurate. And the way to do it is, well, instead of using 3 rectangles, use more. And that's what we're going to talk about here. Is in order to get a better estimate, we're going to increase n. And so what happens then, as you increase the number of subintervals, the number of approximating rectangles is going to increase. Now what happens is those approximating rectangles are going to get very thin. And so what happens is these approximating rectangles then are going to give us a better representation for the region under the graph. And if we let n really increase, so as n increases, as n gets really large, as n increases, the rectangles are going to get thinner and thinner, and we're going to get a really good representation for the region under the curve. And so what's going to happen then is the area of those rectangles is going to give us a better approximation for the area under the curve. And so in this first graph here, what these approximating rectangles are telling us or giving us is essentially a Riemann sum from, well, I equals 1 to, say, n, for just some arbitrary number of rectangles, of f of xi star times delta x. So that's our Riemann sum. It's really the sum of all these areas here. And so if we let the number of rectangles increase, they're going to get really thin. There's going to be a whole bunch of them, and they're all going to be really thin, and it's going to give us a nice, good approximation for what the region under the curve looks like. And so these Riemann sums then, as we let n increase, are going to give us the exact area under the curve. And so if we could calculate the limit as n goes to infinity of the sum from I equals 1 to n of f of xi times delta x, we're going to get the exact area under the curve. And this is our definition for definite integral. So the Riemann sum is giving us these kind of rectangular looking representation for our region, and as we let n get very large, as we let n go into infinity, which we know how to do, that's the limit as n goes to infinity, what's going to happen is those rectangles are getting thinner and thinner, and they give us a better representation for the area under the curve. And so if we calculate the area of all those rectangles and add them together, we're going to get the, and we do that as n gets really large, we're going to get the exact area for the region under the graph there. All right, so this really leads us to our precise definition for the definite integral. So let f be a function defined on the interval from a to b. Then the way we actually define the definite integral of f over that interval from a to b. So we've dealt with this integral notation before. It's the integral from a to b of f of x dx. What this is actually equal to is the limit as n goes to infinity of the sum from I equals 1 to n, so we're using more and more rectangles, of f of xi star times delta x. And this definite integral exists provided this limit exists and gives the same value for all possible sample points. So left endpoints, right endpoints, midpoints, or just anything kind of, chosen at whim. So for all sample points, we get the same value when we do these Riemann limits of these Riemann sums. And so if this limit does exist, then we say our function f is integrable on that interval from a to b. All right, so there's a lot there. So first of all, just kind of look at the things we know. This is our Riemann sum without the limit sign, just the summation here. That's our Riemann sum, and we're doing the limit as n goes to infinity. So n represents the number of subintervals. So if n's going to infinity, what that means then is that delta x, the width of our subintervals, is going to get very small. So delta x we calculate as b minus a divided by n, and this is the width of each subinterval. And xi star here, these are the sample points. And we have control over those. So usually we're doing left endpoints, right endpoints, or midpoints. But it doesn't even have to be those. Those are just the most common ones that we use. So it's usually those. And we have our interval from a to b. So just looking at all the different pieces here. So the way we calculate this, or the way this definite integral is actually defined, is it's the limit as n goes to infinity of this Riemann sum. Now, it's going to turn out, and it shouldn't be too surprising here, that calculating this limit is usually, in almost all cases, a very difficult thing to do. So, we're not going to really look at how to actually calculate definite integrals using this limit definition. So, when we first looked at derivatives, we had a limit definition for derivative. That one it's also difficult to do, but we could actually do it for some easier functions. This limit definition of definite integral, though, is kind of extraordinarily difficult to do by hand for even modest functions like x squared. So you can do it. We're not going to really look at how to calculate these definite integrals using this limit definition. We are going to investigate Riemann sums a little bit more. But calculating a definite integral from this limit definition is, it takes some time. So it's possible, x squared, x cubed, it's possible to do those. But we want to note, we've actually already seen how to calculate an easier way. So just a little recollection here, a little recall. We already know how to calculate these. So we normally use the fundamental theorem of calculus. Part 2. To calculate these definite integrals. Normally that's the way we do it. So we could technically do it from this limit definition. So it technically, if we can calculate a definite integral, then we should be able to calculate the limit of the Riemann sums. But this is normally pretty difficult to do from this definition. So the way we normally calculate definite integrals is to use the fundamental theorem of calculus part 2. So find the antiderivative and then do the subtraction. Much easier, it turns out, in a lot of cases than trying to do this limit. So fundamental theorem of calculus really makes this a much more manageable problem of calculating definite integrals. But here's the definition. And the question is, how do we know if a function is, how do we know if it's integrable? How do we know that this limit exists? Now that's something we haven't necessarily explored just yet. And it turns out that if our function is continuous, then it's integrable. Or, well, if our function's continuous on that interval from a to b, or we can relax that condition a little bit. Our function could have only a finite number of jump discontinuities. Then it turns out the function f is actually integrable on the interval from a to b. That means our definite integral actually exists. We can calculate it. So this is going to be handy to know that if our function's continuous, we should be able to calculate this definite integral. We could either use the limit definition, or most likely we could use the fundamental theorem of calculus. So the issue here is not every function can be integrated. But what this theorem is saying is that if we know our function's continuous, we're good. So we can integrate all functions that are either continuous on the closed interval or even if they're not all the way continuous, if there's a finite number of locations where there's a jump discontinuity, then we can still do it. So it really helps to have to work with a continuous function. Now, just because a function is integrable means this limit exists, doesn't necessarily mean it has a nice antiderivative. So, yeah, a function might be continuous, which means that this integral, the definite integral here, does exist, but we might not be able to necessarily calculate that using the fundamental theorem of calculus if we don't know what the antiderivative is. So just a little warning here. Careful there are functions which are integrable. It's a hard word to say. Integrable. So we technically should be able to calculate their definite integral on an interval with no nice antiderivative. So there's integrals out there that we technically should be able to do, but the function, if we wanted to use the fundamental theorem of calculus, the function doesn't have a nice antiderivative. And so it becomes a much more difficult task to integrate that function. So a little example, integral from 0 to 1 of e to the x squared dx. Technically, e to the x squared, it's a continuous function, so we should be able to do this. So this is an integrable function on the interval from 0 to 1. But it turns out this e to the x squared doesn't have a nice antiderivative. So the fundamental theorem of calculus, we can't really use it the way we expect. So for this integral, yeah, technically the limit does exist, but we wouldn't be able to necessarily use the fundamental theorem of calculus because there's no nice antiderivative to help us kind of simplify this. Could still use this limit definition, but again, that's also very difficult. All right, so just a little kind of warning there. We want to, we know if we have a continuous function, we should be able to do it, calculate a definite integral, just not necessarily how we can do it. All right, let's try one little example just working with this notation here for our definite integral. So let's express the following limit as an integral for this interval from 0 to pi. All right, so we have this limit. The limit as n goes to infinity of the sum from I equals 1 to n of xi cubed plus xi times sine of xi times delta x. All right, so we want to write this as a definite integral. So we know with definite integrals, there's there's our integral sign, there's our differential, and then we need to put a function there in the middle, and then we need to figure out our upper and lower limits of integration. So the interval is where we get the limits for our integral sign here. So if we're looking at this interval from 0 to pi, what this is really telling us is that the starting is a value is 0, and our ending point is pi. So that means we're going to integrate from 0 to pi. It's another way to write this out. And you can kind of think that in this notation here, this limit with the summation sign, that's really what becomes the integral sign here in our definite integral. And so you can almost think of the summation sign here, the limit really kind of smooths it out. So you could think of this as a sigma that's been kind of elongated. And actually that's what it is. It's an elongated S for sigma. That's where they came up with the integral sign notation. But think of it as like this summation. It's been kind of stretched out and smoothed out a bit. All right, so we have the integral from 0 to pi. The delta x here at the end, that just becomes our dx in this notation. And then we look right here for the function that we're actually integrating. And so the function that we're integrating is x cubed plus x times sine of x. And so if we were rewriting this limit, we would rewrite it as this definite integral. And just a little note, since the function x cubed plus x times sine of x is continuous, so sine is a continuous function, x cubed is a continuous function, so this whole thing is continuous, especially on the interval from 0 to pi, this definite integral we should be able to do. So this definite integral exists. So that was all for this example. We're just rewriting this limit notation using definite integral notation. Just a little practice there. All right, so in the next example, what we're going to do is we're going to calculate a Riemann sum. So just kind of going back to the definition, yeah, it's difficult to calculate the limit as n goes to infinity for these Riemann sums. But to just calculate an individual Riemann sum, that's something that's not too bad. So we're gonna see that in the next example. So we'll see you there.